Welcome to the second part of the dependently typed language implementation lecture. Before we start with the main lecture, there were some comments about binding and the De Broglie notation. So I can go through that just to clarify how that works. Let me see. In the De Broglie notation, so what we do is we're trying to. Okay. Oh, glad you could join us. So we want to have a nameless representation of our binders. So what we're doing is let's see. So the problem happens. There's two kind of main cases when the problem happens. One case is when you have something like, I don't know, lambda x to lambda y, I don't know, lambda y to x. So something like this. And if you want to do a renaming and you rename the x in here, then oh wait, no, this is wait, shit. Was that the right example? Yeah. So you want to rename it, and essentially you you can change this notation to lambda 1. We're counting from 0. So this essentially means that this one means that we have to count the binders, and we're going, this is the 0th and this is the first. So a simpler case would be the identity function x to x, and that gets translated into lambda 0. Wait, sorry, 0. So if we apply it to something, 0 means we're using this binder. And here we're skipping out. I don't know. Does this make more sense? What the De Broglie indices are? I'm not the best explaining them. Okay. Anyway, let's start with the main one. So we've left off at the dependent types demonstration. So in this lecture, we'll look at the first of all, how we're going to implement the dependent type rules, which we've seen last time, and we're going to play around a bit with it, and then we're going to extend it. We're going to look at some common types like naturals and vectors, and then have a look at equality and maybe some proofs if we have time.
Like the theme you used last time, so you can see like the comments or like the signatures.
Say what?
Oh,
yes, sure, yeah. Customize. What was the command I used? Shoot. Oh, yes, yeah, maybe that as well, yeah. Customize themes. Oh, yeah, here we go. Space mark. Cool.
There's a lot of like the variables.
That's still that kind of, it's not really showing the entire thing. Is the projector thing? Is there any way to modify that? I think projector is making it too big.
But it's not that I still like the contrast between like.
Oh shit! I think this is the font we used last time. Let me try and see some other one. Improvement?
Yeah, that does, because I can see the code.
Something which is not inverted.
Oh, yes. Yay.
Yeah, that works.
Cool. Right. Yep, and you can see the code. Cool.
I have to move it a bit now because we can't see like the first.
Oh yes, yeah, it's possible to.
Yeah, fine. Or maybe just swap the slides with the code.
Hmm.
Because then we can see.
Good point.
Yeah. that would be-
Cool. Oops. Right. Okay. So we're getting some notation. Okay, there's a lot of stuff happening here because also we're going to have some other primitives in the future. So right now, what we need to focus on is just kind of like for the most part, we only have a few initial constructors, which are important ones. So we're using the syntax in the previous language and extending it with a few new things. So let's just match the slides in this. So we want to change our annotated term. So previously it was term and then followed by type, and now both of them live on the same level, really, even though, well, technically this should still be kind of, some form of type, star. Otherwise they won't type check, but technically they live on the same level. So we're adding a case for star, which is fairly standard, and we're adding one for the dependent function space. And the idea is that the first term, it represents the domain of the function. So like for all x of something, that's this x. And the second one is the range. And the second one can be dependent on the first one. Extending the values, you can see what that means is that the first one is just a regular old value, the x, but the second one, we're using higher order syntax to represent it, and essentially it's a function which it takes the value and returns the expression. Right. Let's see, is there anything else? Then the next thing worth looking at is the type inference, but we can also look at the evaluation first.
Am I correct here that
Oh, yep.
we can define user-defined dependent types in this system because they are all, in a way, hard-coded into the AST, like a vector or
You can. So, for example, okay, let's. It's a good question, and we can talk about this representation and what alternatives there are. So, an easy way of doing things, the classic way, if we want to go completely low level, you can use church encoding. But church encoding can be quite obscure to read, and also it doesn't dependently type church encoding. So the next alternative would be to implement some kind of data types primitive elements for just the very, very basic primitive elements. Like, in Haskell, we can construct our data types using the basic constructors, and you can just kind of do everything manually. You have your unit, your voids, you can do your sometimes, product types. So that's the second one. Of course, the basic algebraic data types are reasonably straightforward to implement, but if you want to have JDTs, for the first presentation, I thought that would be quite involved, and we'd need a few more hours to do so. So in this case, we're going to have our base types as the we're going to have some going to add some very simple types, so like naturals and vectors, not to be confused with some type in calculus. And you could still define types within your language. It's just using the primitives which we got. So you can define a type from vector to nat or from nat to fin. But syntactically, once we're on the object level, even this will give you intuition for how it works. So when you want to implement the next step, which is having your own data types, JDTs, then it'll be much easier. So yeah, let's have a look at how we changed the evaluation. Oops. In evaluation again, let's see what was changing. So again, you have the evaluation for star, which is nothing interesting happening there, and the evaluation for the pi type. Let's see. Yeah, it's missing a slide for the evaluation here, which is unfortunate. Okay, so essentially we take it apart and we evaluate the domain ty, and then we separately evaluate the range, which here is t1, and then we do so in the while we're extending this parameter is we're extending the context with the value x that the range is dependent on. So is this rule straightforward enough? Essentially, yeah. Two things happening, and then so the lambda x is where once we evaluated the function body, we put it back because the vpi constructor, it needs to get a function. So really, the main stuff happening here, and the entirety of this thing is just managing the context.
Can we have type synonyms in signature expanded? What is name and value? I believe it's just a list, but it's not obvious from type signature.
Oh yes, let's have a look where I've put them. Is it here now? Main. Where was it? Environment. Oops. So is it enable name env? Okay. Right. We're trying to remember what it was.
It's common HS here.
Common?
Common HS, I believe. It's defined in there, but
Oh, of course, yeah. Right. So yeah, name can be either a global name, or which is a string, or a local name, which is the De Bruijn indices. And again, just hopefully I explained it. Then so here we go. This result node, and then this is name env, which is the name followed by whatever we're parameterizing name env under. So in our case, we're using the values. So because that's our context, we have some names and they refer to values which need to be evaluated.
env is
Mm-hmm.
the second environment, which is just env
Yeah.
score.
It should be, as far as I remember, just a list. Where is it defined? Wait. PIST. Okay. Here we go. Yeah, just list the values. Yeah, that's our context. So in this case, we have this essentially, we're pattern matching D, which is the big thing, and we split the, oops, split them. So D is the list of which we're extending with X. So we're adding one more thing to the list and putting it there. And yeah, E is the name. Okay, so was there anything else there? I think, yeah. Let's look at, so yeah, just these two rules essentially, and our evaluator is done. And again, just to reiterate, we evaluate the domain, and then slightly complicated thing evaluates the range, and then turns it into function type. So next thing is the inference. Okay, this is the meaty part. This is the okay. Oops. Check. So let's see. First, I guess this we do the annotation rule. So essentially, again, this is a very direct translation of our type syntax into the code. Our goal here is to return ty, so we're inferring, we're inferring the type. And we start by doing it. First, we check that, so ctype, that's type check. We're type checking the annotation we're given. Make sure that it's actually has coin star, so it's an actual type versus some term. And if that succeeds, then we evaluate what we're given, because it might not be in its normal form. And we're using here the empty context to evaluate it. And first G, that just takes the the first part of G, so name and value.
So what's in the first and what in the context?
Name and value, so this is just its name and value. And the context is, well, we don't need it. We don't need a context to evaluate that part.
But what do we normally store in context?
Oh yes, just our this thing. Just a list of values.
What does it mean?
Oh, I see. So.
Are they corresponding to De Bruyne indices, or what is their purpose?
Yeah. So So here, it's to it's the names. So yeah, and the.
This context is not the gamma, right?
Mm-hmm. Oh no, so yeah, that is context is gamma. So essentially, everything we've put in the context is there. Sorry, yeah, there are synonyms.
So if the context is the gamma, then what is the name and?
So that's just our representation for the context. So okay, have a look here. We have, when we build a context, we do so by, we start with empty context and then we add x of type t. And we give it a name. So for global variables, we're using names within the context.
So if you look at the prelude.strlp, that's the name that we do in the let.
Yes, yeah, exactly. That's how we add things to the context. Let's see. I guess you could also maybe use a reader monad if that makes sense. I guess it's a more simple implementation than that.
So why cannot we do C eval of tyt with existing context? Why should we remove it? Why cannot we just use G here?
I guess. Oh yeah, so this is just the type that ceval expects. So we want it to be general enough that we can use it to evaluate.
Why cannot we pass full G? Why should we clean up context in this call? Why cannot we just pass G as is?
Let's go into ceval and see if that helps. So, oh wait, no, it's an eval. Eval. So so which rule would that be? If we're in the annotation and we do TYT, so we are evaluating whatever annotation we have. Let's see. And I guess well, could really be anything. Oh, I see. Yeah, sorry. Yeah, so we're because in this case we're just looking at the local representation. So we don't really care about the global representation in this case. So the local representation will be part of the thing we're evaluating, and then we don't need the global context there. The De Bruyne are the bound variables are the local ones for which we're using. So the bound variables are the parameters. They're the ones that say like lambda x to x. So x is bound, and then lambda x to output nat. Then nat will be the global representation because we're using the name. Does that make sense?
Okay, names are stored in name environment.
Yes.
Yes.
Yeah.
Okay.
And then something like lambda x to x, that we transfer to De Bruyne indices. So that's going to become that form.
Yeah, so all lambda bound variables will be stored in the context, and all top level binders will be stored in name.
Yes, lambda bound stuff is all the top level stuff is in the context.
Top level stuff is in the that's in the name, right?
The name?
Name contains De Bruyne indices as well, as far as I remember.
Yeah.
So
Yeah.
So that's not clear for me. It seems that it includes local
It's like the
indices as well.
concept is not charged, no?
Oh, say again?
It's like the concept is not used because it just takes the first part of the sequence. So the concept is.
Yeah. Really, the main thing is that maybe it will make sense. So let's just keep going. Once we see a different rule where we're actually using context, I guess distinction will hopefully make more sense. So.
Could you please swap them again?
Oh yeah, sure. Sorry. So here we're checking the type of the expression. So it's this part represented in the code here. That's the De Bruyne level at which we are on at this stage. So here, essentially, you can see there's two of these functions, and it starts with I type 0, and then it's like we're on the 0th De Bruyne level. And then whenever we go deeper into the lambda nesting, we increase it by 1. And we keep track of that using this int. So here we pass it, and then we give it g, and then the expression type. And if it fails, this is the result type monad, or if not, then we're returning the ty. And again, the rules for type, super simple for star. And okay, the trickier one is this new one, pi. So our goal is to make sure that the product function expression we're given evaluates to kind star. So to do so, we evaluate the domain, so here we go. P is a domain, and well, first we check the domain that it has star, and then we evaluate it using this line, and then so here you can see an example where the context becomes relevant again. because we are extending the so in last one where we're extending the context here, we need to extend it with x of type t, which is going to be our evaluated domain type, which we're using as an input to the range. And again, this little bit of a thing here. So because we're going a level deeper, we're increasing the De Broglie index. And we are, again, taking this value in context and extending the, here we have the, adding this name, the local plus index, which is our nameless representation, and we add its value, which is the type, ty, in this case, our evaluated form. So we add that to the context. And we do a substitution. So here we do the application. We have let's look at the substitution function, and then here we go. Again, most of these are gonna become relevant later. Essentially, we have something we have the level that we are on, and we have the thing we're substituting, and we have the big pi term. And for example, we call it recursively to go on lower levels, and in the case where we're looking within the function, we're increasing the level by 1. And yeah, essentially this kind of once that's done, we're just checking that the C type extended with the context, and the evaluated thing type checks to V star. So that's this part. And if we know that it type checks to V star, then we know that so it's kind of like if we know that the dependent function type checks to V star, then we know that this thing in the bottom, well, if we know that, so the input type checks to V star and the range is star, so then the whole thing, we can infer that it's a star. And we return the star here. Let's see. And the abstraction case, let's see. So here we go. Kind of modification is very similar to what we had last time, except now we're dealing with the dependent type. So first we infer the type here, I type IIGE1, left-hand side. Then we pattern match on the type we're looking at. And so, for example, in the bad case, let's say we're trying to apply something to not a function. We're applying a non-function term to a term, like 3 applied to 2. It doesn't make sense. So then we give the type error. But hopefully, if it is a function, or a dependent function in this case, then we know that we can apply it. And then the type of application will be analogous to the type of the simply typed version. That makes sense, right? So if we apply, if this is on the left is a function and to the right is an argument, then the result is whatever the type of the argument is. So that's our type. Typing rules. Let's see, is there anything else left? Oh yeah, and we have a few rules, or did we do these? Oh yeah, and the little bit of a case there, once we're checking, so this is the bottom slide, here we go. So this part, if we want to go from inference to a check, then we're doing it in the setup function for the checking, and first we infer the type, as we have in the bottom, and then we do the equality check. We make sure that the thing on the bottom is the same as this thing on the top. So, you know how we were discussing the equality stuff? That's kind of one way it becomes relevant. So, and one way the name becomes relevant because here we're just using very basic syntactical quality. And of course, we can't check functions in Haskell because we're using higher order syntax. So we're using the quote function, which essentially the quote function just kind of like transforms it into from Lambda application into syntax we can check. Where did I get it from? Oh yeah, it's some file. So the quote function is the only like really interesting bit is the VPy part. Everything else is just and the lambda. So essentially we strip away. We generate free variables and we go from the higher order representation, the syntax representation, to more. So yeah, here we have your some value and a function, and then yeah, here these parts we translate them. Function applied to whatever's in there.
So why do we need to compare quotes?
Yeah. So we're just making sure that the types actually our types match. So okay, so we start with we have an expression and some value of a type, and we are checking that the value matches the type. So we can do inference where we generate the type, or we can do type check where we're already given a type and we're just making sure that.
So is this implementation of that rule, or is it something different? Because the rule says just okay, get type and return type. So like doing some additional validation, or what's the reason to?
So this is the implementation of the CHK rule, right? And essentially, yeah, we're inferring the type. Like if we're in a case where we can infer a type, and we want to use that in a case where we need to check a type, then this is what the checking rule is for. And essentially here, the code is just a translation of that, where we have our expression, and we perform type inference on it. Oops, sorry, as on the top case. And once we've performed the inference and we know what the type is, which is v1, we can use it with the v which was provided to the function that we want to check.
Yeah, but it's kind of
underscore stands for?
Yeah, this just sort of so okay. If we go back to the AST, and oops, inf is how we embed. So we have two term constructors. We have iterm and cterm.
Yeah. And inf is linked to iterm.
Yeah.
And type inference on iterm is basically trivial. Just extract its type annotation.
For the annotation case, yeah. For the other ones, the type inference has trickier rules.
Iterm is checked on the annotation rule. If you run ctype for iterm, then it will just extract its annotation.
Well, iterm is you're close. I think iterm is checked by all of the rules which have arrow upwards. So all of the ones, if there's on the bottom, it has the judgment that the arrow goes upwards, then this is what iterm is used for. The cterms are used for the type checking rules. Like some implementations don't split them, some implementations just have one collection of terms, but this is a popular way of implementing it, just to make it easier. So all of the ones on the top are using iterms, and the ones on the bottom using CHK, but because we have the CHK rule, anything which we can infer, we can translate into a check. Because we've inferred it, so then it's trivial to check it, because we've done the work already. Like if we've... and so to translate it into code, that anything which we've inferred, we can easily check, we use this inf data constructor within cterm. It's just a way to put our iterms in there. So were you thinking that iterms only refer to the annotation rule? Okay. Yeah. So all of these really we do iterm within it. So infer in. So annotation, that's the trivial one, and then there's also star, which is this case, and then the product one, which is this case. And then we're just, once we've done a type inference on that value, and again, this assumes that we can infer this type. So, but if we can, then we compare it to the given type and see if it matches. So we're giving an inference to the compiler, performing inference, and then we're also giving it a type to check. And yeah.
Wouldn't it make more sense to, in the math, infer that it's like t prime and then require that it's equal to t, just like in code, or? Because in code, you're inferring that it's v prime, and then
Yeah.
you're comparing v with v prime.
Yes.
But in math, it's just like magically equal. In math, like this t and t seems to be just like magically equal or something. How does that?
Yeah. So this really in the math it assumes like in the math it kind of it assumes that we're going to be using these rule. Well, it's not so much as they're equal, so much as you can think of the top hand as the input and the bottom as kind of like the output. You know, it's the rule says if we have a situation where we can infer the type, then symmetrically we get the situation where we can check it, because there's no reason to not be able to do it, because we've generated the type, so now we can check it. It's trivial.
In Haskell, your input is the term e and the type t.
Yeah.
Right?
Term e. Yeah. And
Or type v.
yeah, the term e and then type v. Yeah. So we could just go. We could just run the check that see if the e has type v, but if let's say in a different case, if we just had some arbitrary case, like we could do this and we just say let's check if e has type v, but specifically This case inf underscore refers to the case where we are able to infer the type. And then we're checking that the type we're inferring is matching it, the type we've given. Does that make more sense?
But this inf provides you with the knowledge that you can infer it.
Yes, yeah, that's the situation. Where if we're able to infer it, then that's what we're really going for here. That's what we're using the representation for, essentially. C terms through this rule, essentially they subsume I terms. So all I terms are valid C terms. And essentially inf just saying we're dealing with an I term, but we want to convert it in the C term case. So somewhere out there, the only way you would have inf underscore is because somewhere else in your type checker you've inferred the type, and then you've made it into a C term by prepending it with inf. Maybe if we have a look for, oops, when do we generate these? Let's see. Well, I guess, yeah, if we have one. Not really converting it anywhere here, admittedly. In an eval, are we doing this? Okay. So it's not really been something we've used much, but in principle we could if we needed it for some reason. So,
in principle, when constructing an inf node, you could then infer the type and save it inside of the inf constructor.
yes, yeah, exactly. Yeah. So if yeah.
Doing it when you're using it.
Yeah. So in here we're not constructing a typing derivation where that was necessary within our algorithm, but we could if we had, like, let's say more things going, different rules, and then we really needed that, then yeah, we could do it that way. And lastly is the checking of the lambda rule. Let's see, so C type, point index context, lambda E, and then the product type. So we have some we're checking that the we have a we're checking that in the context lambda x to some expression is a dependent function type. And of course, again, the question is, how do we do that? You might remember from yesterday is we take this E, take the body, and kind of make sure that we can derive, we can check that it has type tau dash in this extended context with x. And yeah, so here we have the extended context, and here we have the type we're checking against in this extended context, and let's see what notes are. Yeah, we're putting the bound x into the context, and we perform a substitution within the function body, because yeah, we're substituting the thing we're bound. Right. So, these were the typing rules. Let's see a demo of this. So, what would be a good demo. Let's implement something. Let's implement something from scratch. At the moment, so we don't have much. We haven't the language has the other constructor, but we haven't covered them. We're going to cover them later. So for now, we're just going to implement something which we can do even in this case. So let's implement the identity function. It's the classic one. So if I implemented it, okay. Let's just close this and start over. So let ID equals. Let's do this interactively, testing you guys' knowledge. What goes in? What are we gonna put in? Yes, yeah. So first we need to, we're getting a type as an input. So A will be the type parameter. And then, yes, so that's X. And then we have the output. And what's the output? Yeah. And then we're typing it, which is for all. A has type star. And from that, we go to for all A type star. What happens then?
X of type A.
Yep. And we have X is of type A, and we get as output X. Was that it? Oops, no. Shit. Type X of type A. Oh yeah, A to A. Wait, no. Okay, that's a bit inferred. Okay, here we have our type errors. Type inferred. Okay, these are not the best type errors. Oh, of course. That's a good point. Oh.
So first take something of type star.
Yes, yeah. Take something of type star, A star, and then take X of type A, and return X. Oh, okay, cool. I guess, yeah, we'll continue this after the break.